In this video, we go over section 14.4 on the chain rule. So in calculus, the chain rule describes how we can take the derivative of a composition of functions. So first, let's see how we can have a composition of functions when we have multiple variables. Right. So for example, let's take f of xy as a function of two variables, x and y. And then the variables x and y each can then be functions of one or more other variables. So as an example, let's keep things simple, right? So we'll take x and y as just functions of a single variable, say t. And a situation where this can occur is when you have a vector valued function that say represents a curve, right? So for example, we have a vector valued function r of t, and here we only have two variables x and y, so let's take a two-dimensional vector, and the components are x of t and y of t. So when we have these two functions, right, so the f, the function of two variables, and then r, the vector valued function, we can combine them in the following way, right? So here the vector valued function takes the single variable t as the input, and it outputs the components x and y, right? So the output here is going to be my x, and the output here is going to be my y. And because it outputs the two variables x and y, I can use that and plug it into my two variable function in the following way, right? So we substitute the vector valued function into f, right? Because I'm allowed to do that because for the inside function, the output of the inside function should be the input for the outer function, right? And that's exactly what happens, right? So here we have x and y as the output, which in turn becomes the input for f. And then so ultimately the x coordinate here is just calculated as x of t, and then the y coordinate here is just calculated as y of t. And then so this is an example of a composition of functions where we have this function f of two variables. Okay, so here, once we perform the composition, f is then ultimately a function of a single variable, right? Because t is essentially the input here, and then f is the output. So we can ask ourselves, okay, so once we perform the composition, how do I differentiate f with respect to t? And so that's essentially what we're going to do with the chain rule. So the thing to be careful about the chain rule is that, so here I give a specific example where f is a function of two variables, and then each variable x and y is in turn a function of only a single variable. So depending on sort of the combination of the number of different variables involved, right? So we can have a different example where f is a function of x and y, and then say x and y are in turn functions of not a single variable, but say like two variables, s and t. And then so for each kind of derivative that we're trying to determine has a slightly different chain rule. But luckily, all the chain rule formulas sort of follow a pattern, and it's not too difficult to write the appropriate one down for whatever situation you're dealing with. So again, just like this situation here, the chain rule is useful when you want to combine a function of several variables like this with a vector valued function that represents some kind of curve, or later on in the course, even surfaces. I can actually describe geometrically what's going on when you do a composition like this, right? So geometrically, the function f of xy represents a surface, and then the vector valued function r of t represents a curve. And so by doing this substitution like this, essentially what you're trying to do is you're trying to trace out the path of a curve within the surface that's represented by the graph f of xy. So I don't have a lot of space here. So like maybe I can just try to cram it into the corner here, right? But imagine you have some surface here. So that this is not the entire surface, but this is a portion of the surface, right? So let's say this is the graph of f of xy, and then within the surface, you want to trace out some kind of curve, say c, and so you can do that, right? So you have a vector valued function representing the curve c, and then by doing the composition here, that's exactly following along this path within the surface represented by the function. Okay, so that's the basic idea. So we want to be able to differentiate these kinds of expressions with some kind of chain rule, and so the chain rule for this specific situation here, where f is a function of two variables x, y, and then x and y are each functions of t, right? So then the chain rule is described here. So basically, you can think of the chain rule as like this, right? So f is a function of two variables, so it has two partial derivatives, one with x and one with a y, right? So that's where the df dx appears here, and then the df dy appears here. But then once you differentiate with respect to x, x is in turn a function of t, so you can also differentiate x with respect to t, right? So that gives you the first term, and then so similarly you have the partial with respect to y, and then taking y, you take the derivative with respect to t, and then that gives you the second term here. And then again, both of them end up being with respect to t, so then you can add them together to get the chain rule to calculate df dt. So we get the chain rule formula here. And so if we change the number of variables, right, so here if we keep f to be the same, so two variables x and y, but then instead of being just functions of t, we can have x and y be also functions of two different variables. So x is a two variable function with s and t, and y is also a two variable function with s and t. So then now if you perform the substitution, right, so like it'll be f of x of s comma t, and then you plug this in for y, right, so y of s comma t, right? So then f is then ultimately a two variable function of s and t, and so it makes sense here to ask, okay, so now you can differentiate f with respect to s and also differentiate f with respect to t. So each of these two partial derivatives, so they're separate, right? So you have df ds, and separately you also have df dt. So each of them have their own chain rules, and so this is the chain rule that determines df ds, and then this is the chain rule that calculates df dt, right? So you can see that they're mostly similar, right? So here, because f is a function of x and y, you have two terms, containing the partials with x and then the partial with y, but then for each of them, again, because ultimately you're trying to differentiate with respect to x, you also have dx ds and also dy ds. So dx ds goes in this term here, and dy ds goes in this term here. And then similar, when you're trying to determine df dt, you have the chain rule like this. Okay, so even though each of the chain rules is slightly different, there's similarity between them, and essentially each chain rule formula can be remembered by constructing the following tree diagram, right? So at the top, you have your outermost function. So in this case, my function f, right? So this node represents the function f, and then you branch out depending on how many variables f has, right? So here f is a function of 2 variables, so we branch out to x and y, and similarly here, again, f here is a function of 2 variables, so you branch out x and y, and then each variable x and y might also have some number of variables. So in this case, x and y only has a single variable t, so from x you only have one branch t, and then from y here you only have one branch t. If they're functions of 2 variables like here, then each x and y branch out to 2 variables s and t, right? So this diagram represents this chain rule here, and then this diagram represents the 2 chain rule formulas here. Okay, so now how do we use the diagram to write down the appropriate chain rule formula? So in the first example, again, you ultimately think of f as a function of t. So it makes sense to ask, how do I differentiate df by dt? And so here in the numerator, you're starting with f. In the denominator, you're trying to differentiate with t. So in the tree diagram, you collect all branches. So starting from the top node all the way to the bottom nodes, you collect all branches that go from f all the way to t, right? So here I start from f, I end up with t here, and if I start from f here, I also end up with t here, right? And so this branch here represents this first term, and then this second branch here represents this term here. And okay, so how do I write them down, right? So each derivative here is one part of the branch going from node to node, right? So from this node to this node, you're differentiating f with respect to x, and then from this node you're differentiating x with respect to t. So collecting this, you get this. And then following this path, differentiating f with respect to y, and then differentiating y with respect to t. And that's exactly this term here. And then similarly for this diagram here, right? So ultimately f is a function of s and t. So it makes sense to ask, okay, so how do I differentiate f with respect to s, or separately f with respect to t? So once you construct the whole diagram, right? So to get df ds, you follow along all branches that start from z and end up at s. So there's 2 possible paths, right? So this path here, and then this path here. And then each separate path is added together, and then within the path, that tells you how to write down the derivatives, right? So dz ds, or df dx, dx ds, df dy, dy ds, right? So that's this formula here. And then for t, this starts from f, ends up at t. This starts from f, ends up at t. F is the same as z, right? So So you get df dx, dx dt, plus df dy, dy dt, right? So these two paths put together form this chain rule. Okay, so that's the basic idea behind the chain rule, and then specifically here where x is a function of just t, and then here x and y are functions of s and t.